Hello, welcome to this video. So I'm recording this in the summer, so I wanted to do a nice light video. And so for this video, we're going to be harking back to the days of ancient Greece, and we're going to be looking at a bit of ancient Greek mathematics, although doing it in a modern perspective. And particularly what we'll be doing is we'll be having a go at finding the volume of a cone. And it's a nice piece of practice for integral calculus. Usually integrals are associated with areas, but if we integrate over areas, if we integrate areas over distances, we end up with volumes. So we might have seen that when doing volumes of revolution, but an integral will take us from the dimension of the integrand to one dimension higher. So if our integrand is just a curve, then our integral will give us the area under the curve, but if our integrand is an area, the integral will give us some kind of volume. And we'll be looking at the volume of a cone in this video. Now, the idea of the integral is often credited to Newton and Leibniz, but actually the maths of integral calculus, although they wouldn't have phrased it as integral calculus, actually goes back to ancient Greece, which isn't too surprising when you consider how much of maths in ancient Greece was related to shapes and geometry, so it's quite natural that integral calculus would develop within ancient Greece. The formalism that we use today come a lot later with Newton and Leibniz, particularly. I think it's Leibniz's notation we tend to use. But the actual ideas of integral calculus were known to ancient Greeks, and they knew how to get the volume of a cone. And so that's look back at how the ancient Greeks did it, and how we would also do it today, although using slightly different notation. So we've got our cone here, which I've drawn very badly, so I will draw the cone once more. You can tell it's early morning because I can't even draw cones. There we are, that's another badly, but back to drawn cone. And if we take any segment on this cone, so any region of it, we can say, we can draw, essentially a circle around that point. If we slice our cone, horizontally, we get a circle, which is why a circle is a conic section. And if we go a bit down below and look at the volume of this segment looks pretty similar to a cylinder. So this segment is close to a cylinder if its width, which I'm going to call delta H, is small. And the volume of this cylinder, which is approximating the volume of this segment, is given by the area of this kind of surface. So we get our surface area here times delta H, or times the width of our section. But the area of a circle is just pi r squared. So if the ith segment has a radius ri, then the volume of the ith cylinder, so I'll put cylinder comma I to indicate the ith cylinder, is pi ri squared delta h. Or we can just shorten that to the volume of I, but V of I is the volume of the ith cylinder, is just pi ri squared delta h. Now our kind of cone, we can get the volume of our cone by essentially summing up the volumes of our cylindrical segments, or nearly cylindrical segments. And so we can say that if the width of a segment is small, then the volume of our cone is approximately equal to the sum of all our kind of cylindrical segments. So the sum of I, well, the sum of VI, where VI is the volume of our ith segment. Or if we write it explicitly in terms of the radius of the ith segment, the volume of a cone is approximately the sum over pi ri squared delta h. And the Greeks realised, and they were able to get the volume of a cone from this statement, the Greeks realised that the volume of a cone could be given exactly if we made our segments perfectly cylindrical. And to do that, we need to have an infinitesimal width, so it's that we don't have slanted sides in our segment. In the case where this becomes infinitesimal, so we would use dh today, or we could use 0 because they're infinitesimal, these segments become perfectly cylindrical. Because the width goes to 0 or becomes infinitesimal. And so the volume of a cone is given exactly by the limit as delta h goes to 0 of the sum of all our segments, but now we have an infinite number of segments because, each segment is approaching 0 width, but all the segments together make up a cone with finite volume, so we have to have an infinite number of them. If we have a finite number, we give a finite number of segments and then a infinitesimal volume for our cone. So to prevent having an infinitesimal volume of our cone, we need an infinite number of these infinitesimal segments. And then the rest of our formula stays the same. So essentially we can get the volume of our cone by making the segments really, really thin and stacking an infinite number of them. And the ancient Greeks knew how to evaluate this kind of limit, even if they wouldn't think of it in terms of limits. And we're going to do something similar today. Now, in the language of how we do integral calculus today, we would write this volume mildly differently. We have a special symbol for sums that are continuous. So sums where we're summing infinitesimal things an infinite number of times. Well, when we're summing an infinite number of infinitesimal things. And the symbol we use is the integral. So we would rewrite the volume of a cone as being equal to the integral from pi I squared dh. Now dh is the limit of delta h as delta h goes to 0. So it's an infinitesimal width of our segments. And to make maths easy, we can have all segments having the same width, which is why I write dh rather than dhi. There's no need to put an I there because all our segments have the same infinitesimal width. And so now we need to evaluate this integral. Now usually when we're doing integrals, there are some exceptions to this, but generally we would want the thing that we're integrating, so the function within our integral, so this, to depend on the same variable as the thing we're integrating over. But we can clearly see that in the middle, this part depends on the radius of the ith segment, whereas this is referring to the width of the ith segment. So they're not dependent, they're not referring to the same variable. So what we would really like to do in order to evaluate this integral to find the volume of our cone is rewrite r in terms of h. So we want to find essentially this function. R is a function of h. And that's what we're going to do now. So I'm going to leave the integral we're trying to solve. And we'll try to find what this RH is. Well, to do that, it's important to know something. So what I'm doing here is I'm looking at my cone in one case where I have the cone base has a radius of now small r because I'm essentially cutting the cone, and it has a vertical height small h. Whereas my overall cone from the tip to its base, let's say my cone has a base of capital R and a vertical height capital H. It's important to note that we can form a right angled triangle from both of these. And if I make these a bit bigger, it's perhaps easier to see. And the right angled triangle is actually similar for both cases. So in one case, we have our segment here, but we're going to take our measurements to be across the entire cone that we're trying to find the volume of. And I'll put these measurements in green so we can more easily see them. So our entire cone has a vertical height of capital H and a radius of capital R, whereas the distance, whereas when we kind of cut a cone at the segments, so we kind of generate, if you like, another cone, but a shorter one. This cone, well, we've said that the bottom radius of this kind of, if you like, truncated version is small r, and it has a height h. Well, because the side of our cone is kind of at a constant slant, no matter where we are on our cone, this angle and this angle are going to be the same. And what that ends up meaning is that these are similar triangles. So essentially, the ratio of the vertical height to the horizontal distances are the same in both diagrams. And the key thing is, for our kind of cone that we're considering, our whole cone, capital H and capital R are fixed. They're referring to the cone as a whole. They don't depend on the segment we're talking about. Whereas these things do depend on the segment, but we can now rearrange our equation here, and we can say that small r is a function of small h, so the radius of the ith segment as a function of the height of the ith segment from the top of our overall cone is given by, so if we do a bit of rearranging, we'll get r times small h over big H. And we can now substitute this into our integral. And this will make our life, well, of evaluating this integral a lot easier. So we now got the volume of a cone is integral of pi, but now for r we've got capital R small h over big H. We'll square that dh. Now I've dropped the I. I could have write this and hi to emphasise it's the ith segment, but now I've used small letters to show. I'm using small letters to show when we've got our segments, and big letters to show when we've got our cone as a whole. So we don't need the I anymore, because our small letters do the job of telling us if we're talking about a segment. Now, the only other thing we really need to do is to work out the limits of our integral. So we integrate in terms of height, and the height at the top is 0. So again, 0, and the height at the bottom is capital H. And remember, capital H is the vertical height of our entire cone that we're trying to find the volume of. And so now we just have to solve this integral, and it's a fairly straightforward integral to solve if we remember capital letters are constant because they're referring to fixed properties of our overall cone, not to the segments which are varying across our cone. So if we take out, pi and our other constants, we have this. And then we can use the fact that integral of, say, x squared is going to be x cubed over 3, and we can exchange x for h, because x is just a variable letter we often pick, but it doesn't matter what letter we give our variable, it follows the same rules of calculus. So we can rewrite this as h, small h, small h cubed over 3, and we're integrating between 0 and h, and that will give us pi r squared h cubed over 3 h squared. And then if we cancel out our the capital H as we can, we end up with our volume for our cone. So the volume for the cone is equal to 1/3 times pi capital R squared H. So in other words, it's essentially 1/3 of the volume of a cylinder which would have the same vertical height and radius of the circular base as our cone. Sorry, as our cylinder. The volume of our cone is 1/3 times the volume of a cylinder, where the cylinder would have the same cross-sectional area at the bottom and vertical height as the cone we're finding the volume of. So, this is, I think, a nice calculation to do. It doesn't involve any radical integrals, but it's nice to see how we can use integrals to find volumes as well, and that's part of the reason I'm doing this video, because so often the first time you see integrals, they're commonly just associated with area, whereas what they're really doing is they're really giving us geometry in one dimension or higher than the thing that is going inside our integral. And that idea actually relates to a theorem in physics called Stokes' theorem. And Stokes' theorem actually treats the integral very generally. So we're considering, integrating over something of arbitrary number of dimensions. But anyway, that's everything for this video. I might do a video on Stokes' theorem at some point. Well, I probably will. But that's everything for this one. I hope this has been an enjoyable video. There's definitely less tensor indices than some of the videos on general relativity, but if you enjoy maths and all of that stuff, worth checking out my channel, because I've got lots of different stuff there on different kinds of tensors. Got playlist on linear algebra, and always adding new things. So more stuff is coming up on general and special relativity on the channel, but that'll be dotted around a few other videos like these. But I hope you have a wonderful day. Keep exploring, keep solving maths problems, and I look forward to doing more maths with you in not too long. Anyway, wishing you a wonderful day and stay curious.